All right, so let's get started with the technical session. I'll be chairing this session. My name is Arpit, and I'm an assistant professor at University of California, Santa Barbara. We will start with the first paper, Concordia, where we will learn how we can teach the 5G virtual RAN to share compute. The speaker will be Shenfon Focus. He's a senior researcher at Microsoft Azure for Operators. Prior to this, he held a similar position at Microsoft Research Cambridge, and he finished his PhD from University of Edinburgh. His research interests are in the area of network architectures for next-G, radio access networks, as well as applying machine learning to mobile networks. So can we start the presentation now?
Hi everyone, my name is Shenfon Focus, and today I'm going to talk about our joint work with Božidar Radunović on how to enable the sharing of compute between the virtualized RAN, or vRAN as it is called, and other best effort workloads at the edge. So the RAN is the part of the cellular network infrastructure that includes the base stations and is responsible to convert the data packets into radio waveforms and vice versa. Now, in traditional cellular networks, the RAN appliances look very much like what you see in the picture on the left. They're basically specialized hardware boxes that implement all the functionality that is needed for the whole protocol stack of the base station. However, one of the major changes that 5G brings to next generation mobile networks is the extension of the concept of network function virtualization to the RAN that allows the deployment of RAN functions on commodity hardware at the edge, which could include both general purpose processors and in many occasions hardware accelerators. Now, the reasons for introducing such virtualization capabilities to the RAN are similar to those in other domains and include, for example, vendor lock-in mitigation, flexible upgrades, a rapid rollout of new standards and services, and of course, an opportunity to reduce the cost. Now, in this newly formed vRAN landscape, there are a lot of opportunities to share compute resources between the vRAN and other workloads. And to demonstrate this, we conducted a lot of measurements, capturing real traffic from LTE macro cells in the area of central Cambridge in the UK during busy hours. And more specifically here, you can see a small 10-second snippet of a bigger 1-hour trace of traffic that we captured from 3 cells. And one thing that we observed, and which you can see on the left-hand side figure, is that cell traffic is bursty in nature at very fine timescales in the order of milliseconds. And this is important because the traffic size is directly correlated with the CPU utilization, which means that any idle vRAN periods correspond to unused CPU cycles. Now, from the right-hand side figure, you can see that a single cell is completely idle for about 75% of the time. And even if we pull and process multiple cells together, 3 cells in this case, those are still completely idle for about 25% of the time. Moreover, the median size of the cell's transmitted traffic is 10 times less than the 95th percentile. Now, there are generally many reasons for this bursty behavior of the RAN load, and those among others include a variability in the number of users that are transmitting or receiving, the sizes of their packets, the signal quality, as well as the type of traffic, whether we have uplink or downlink traffic to transmit. But given that the vRAN must be provisioned with enough CPU to support peak traffic, this effect leads to a low utilization and demonstrates that there are many opportunities to share the compute resources of the vRAN with other workloads whenever the cells are either idle or completely or lightly loaded. Now, there are many workloads that could benefit from such sharing, like, for example, machine learning training and classification workloads that have to run at the edge for privacy reasons, workloads for local content caching to reduce latency, and even cellular functions or functions for the orchestration and monitoring of the mobile network itself. However, in practice, sharing the compute resources between the vRAN and other workloads is not a trivial task. And the reason is that the vRAN is a soft real-time system where processing deadlines for packets that are transmitted or received must be met with 5 nines of reliability. And the violation of those processing deadlines leads into packet drops and reduced reliability. So when other workloads are collocated with the vRAN in an uncontrolled manner, it becomes very easy to violate such deadlines. So to demonstrate this, we performed a number of experiments on a commercial-grade vRAN's reference implementation for various vRAN configurations and for varying traffic loads. And in all those cases, we studied the impact of collocating the vRun with other workloads, like, for example, Nginx and Redis. And as you can observe from the table on the left, in all the scenarios that we studied, the average CPU utilization of the vRun was less than 42%, meaning that there were plenty of idle CPU cycles that other workloads could use, at least in theory. However, the introduction of such workloads caused the violation of many vRun processing deadlines, which is what you see here on the right with the dashed red line. And this led to reduced vRun reliability that was actually less than 4 nines. Now, there are two key reasons for those deadline violations. The first one is the OS scheduling latency, because workloads that are collocated with a vRun can make system calls or cause interrupts that in many cases can make the kernel enter non-preemptive sections, effectively delaying the vRun processing. The second reason is cache interference. Other workloads that are collocated with a vRun share the same cache, leading to cache evictions of the vRun data, and therefore to an increased signal processing time. Now, both of those reasons are well known in the literature, and a standard operational practice to mitigate them and ensure 5 nines of reliability is to dedicate CPU cores and cache to the vRun regardless of the traffic load, which effectively leads to a huge waste of compute resources. So to deal with this problem and to allow the statistical multiplexing of the vRun with other workloads, we designed a user space scheduling framework which we called Concordia. And at a high level, Concordia views the vRun as the high priority workload and other workloads as best effort, and it then relies on an over worst case execution time prediction mechanism that decides the minimum number of CPU cores that must be proactively allocated to the vRun at any point in time in order to meet its processing deadlines. And this proactive allocation leads to a controlled processing latency for the vRun workload, allowing us to partially reclaim idle CPU cycles that can then be given to other workloads. Now, in the context of this work, Concordia specifically focuses on vRun deployments on general purpose processors and on the physical layer of the vRun stack, which is responsible for the signal processing operations of the run. And the reason for this choice is that according to our measurements and measurements from other works, the physical layer is the most demanding part of the run stack, generating more than 60% of the total vRun workload. So to explain how Concordia works in more depth, I first need to provide a few more details about how the physical layer of a typical vRun implementation looks like. At a high level, transmissions and receptions of the vRun happen in slots of a fixed duration, and at the beginning of each slot, a set of signal processing tasks have to be processed with some deadline that is typically a few hundreds of microseconds up to a few milliseconds. And the signal processing tasks present dependencies where the output of some task can be used as input to others, forming a DAG structure. For example, here you can see the DAG for downlink transmission, where we send packets from the base station to the users through the radio. And from this example, you can see that, for instance, the rate matching task cannot begin before the encoding tasks here have completed. Now, the signal processing tasks are processed in a set of CPU cores, which we call the vRun processing pool. And the idea of how this works is that the task that is ready to be executed is assigned to an idle CPU core of the vRun pool for processing. For example, here you see the CRC generation and segmentation task. And once this task is completed, the next set of tasks in the DAG gets scheduled using as input the output of the previous task. In this case, we're talking about the encoding tasks. And this goes on for the rest of the tasks. And whenever there are idle cores, other workloads can run, which, as already discussed, can lead to this problem of scheduling latency and cache interference. So Concordia solves this problem by introducing two components, a worst-case execution time predictor and a scheduler. The idea is that the predictor makes parameterized predictions of the worst-case execution time for each signal processing task of the DAG at the beginning of a slot, using a method that is based on quantile decision trees. So basically, each task has a quantile decision tree as a predictor that takes as an input a set of features based on the vRun state at the beginning of a slot. For example, features could be the size of the packets that have to be processed, their signal quality of the users, and so on and so forth. And based on those inputs, we can traverse the quantile decision tree to get as an output a worst-case execution time prediction. And then the predictions of all tasks are fed into the Concordia scheduler, which in turn uses a state-of-the-art federated scheduling algorithm from the mixed criticality literature to proactively allocate cores to the VRAN for the whole duration of a slot. And then any cores that were not proactively assigned to the VRAN can be given to other workloads. Now, the scheduler runs at a very fine granularity of 20 microseconds, which allows it to make corrections in case it observes that we are close to missing some VRAN deadlines. I'll not go into more details about the design of Concordia in the interest of time, but I would encourage you to have a look at the paper for more details. Now, in terms of results, we implemented Concordia using the state-of-the-art commercial-grade VRAN implementation of Intel FlexRAN. And here you can briefly see one of the results that demonstrates the percentage of CPU that we can reclaim with Concordia in the ideal case, where a collocated workload can make use of all the CPU cycles that are being left idle from the VRAN. And as you can see on the left, we can reclaim up to about 80% of the CPU cycles in the case of a low traffic load. But very interestingly, in some common 5G scenarios, we can actually reclaim up to about 40% of the CPU cycles, even in the case of a fully loaded run, which is what you see here on the right. And as we show in the paper, all the collocated workloads that we tested, like for example Nginx and Redis, can reclaim a large portion of those cycles without causing any deadline violations and therefore achieving the target of 5 nines of reliability. Now in the paper you can also find a lot more results about the benefits of Concordia, like the accuracy of its predictor and its computational overhead, but I'm not gonna give more results here in the interest of time. Okay, so to conclude, in this work, we showed experimentally and through measurements that there's a significant opportunity to reclaim VRAN CPU cycles for other collocated workloads. And we can achieve this through a user space CPU scheduling framework that we call Concordia. Concordia uses a novel prediction method for predicting the worst case execution time of signal processing tasks. And it then uses those predictions to proactively allocate CPU cores for the VRAN workload. Now, through our evaluation, we have shown that we can actually reclaim up to about 80% of the VRAN pool CPU cycles without affecting the VRAN processing reliability. Now, as a last note, I want to mention that in the paper, we also discuss other extensions and scenarios where Concordia might be applicable, like, for example, the case of a VRAN with hardware accelerators. So please have a look at the paper for more details. And with this, I'd like to conclude my talk and thank you very much for your attention.
All right, we can thank the author. And we have some questions over Slack for the author. So one question from Rafael is, how would a deadline miss impact the performance when the network is not fully loaded?
So basically, the way that the VRAN behaves is that you have slotted transmissions and receptions, and that means that even when you have low load, and because you have this bursty traffic, there could be only a few slots that have a lot of data to transmit, and the rest could be completely empty, and that would still give you the a lightly loaded network. However, for those slots that you do have traffic to process, if you end up missing a deadline because you had another workload actually hogging the CPU, then this will result in a packet drop, and therefore you will still have low reliability.
Perfect, thank you. So there is another question from Andres, and assuming the availability of hardware accelerator for FTC operations, which offload most of the VRAN load to the pool of CPUs, does Concordia still shows gain over generic schedulers, and to what extent?
Yeah, so the main focus of the paper was on cases of the VRAN running fully on CPUs. We have a study as part of the paper with the existence of accelerators where we show that there are idle CPU cycles that could be reclaimed. So the thing is that even if you have hardware accelerators, not only some of the tasks are offloaded there, and therefore you're still going to be having tasks that will be running on the CPUs and could be affected by the workload allocation. So definitely there could be an issue with tail latencies, and Concordia could be used for improving the efficiency there. This is something that we have not studied yet, but it's part of what we want to see next in the context of Concordia.
Perfect. So I think there are more questions for you over Slack, but like before I let you go, I have a question for you. So you mentioned something about using a user space scheduler, and that got me thinking. Like, so like it's not very intuitive to have a scheduler in user space, especially when we are making really fast decisions. So what is the scale at which this scheduler is supposed to make decisions, and what are the limitations of having a scheduler in the user space?
Yeah, so the scheduler of Concordia is making decisions at the granularity of 20 microseconds. So basically, what it really does is that it checks whether the predictions that were made about how many cores we're going to need for a particular slot are going to be met or not. And if not, it intervenes, just giving more cores to the vRAN. Downside, if you want, of that is, first of all, this kind of scheduler cannot really control the other workloads. So basically, all the other workloads are just seen as best effort workloads that must be evicted if the vRAN needs the cores. The other kind of limitation maybe is that this adds additional overhead because you need to have this scheduler that is running for 2 or 3 microseconds every 20 microseconds, making this decision. So this adds a requirement, to have a core which will be used for this kind of scheduling.
All right, thank you. So SIGCOMM, we do have some more questions over Slack for you. But next we have Hao Lin. He'll be talking about a nationwide study on cellular reliability. And Hao is a second-year PhD student at School of Software, Tsinghua University, and his research interests are broadly in the area of network measurements and operating systems. So can we start the presentation?
Hi, I'm Hao Lin, the second author. For the past decade, cellular network has been the cornerstone of modern human society. However, as its technology rapidly advances, the question of reliability seems to remain unanswered. Today, I want to talk about our work on cellular reliability, involving our nationwide measurement, analysis, as well as practical enhancements. Now, let's first see the problem. From common activities to emerging applications such as 4K video streaming and AR, VR, cellular network lays the foundation of today's mobile ecosystem. With the recent advent of 5G technology, we have started to realize even higher bandwidth and lower latency networks, which significantly outperforms 4G networks in both performance and service availability. However, while we have been mainly focusing on performance and availability, another important question seems to be overlooked. That is, how reliable is cellular network today? After all, performance is meaningless when cellular data connections fail to work. To answer the question, let's first go through our current knowledge of cellular reliability. In general, from a mobile device perspective, cellular data connections can fail mostly in 3 ways, including data setup error, out of service, and data store. In these failures, the device can receive signals from a nearby base station, but either fails to establish actual connections with it, or the connections cannot properly receive cellular data. Unfortunately, till now, cellular reliability is rarely studied due to these 3 critical challenges. As a result, cellular reliability constantly acts as an X factor in discussion or decision making. So, what can we do about it? To close the knowledge gap, we take a unique opportunity to collaborate with a major Android phone vendor, Xiaomi, who serves around 250 million users, to conduct a large-scale study on cellular reliability. Specifically, our goal is to understand the prevalence, severity, and root causes of cellular reliability issues. Interestingly, it turns out to be well aligned with the business interests of Xiaomi, as cellular data connection issues were a major source of their customer complaints but had been elusive problems for its engineers. To achieve our common goals, we need first to understand Android's existing facilities for managing cellular connections. In general, cellular connection management exists as a system service in Android, where the life cycle of a cellular data connection is modeled by a state machine. As state changes, Various problems are monitored by Android's facilities, most of which are related to our concerned issues. Upon problems, Android typically reports the occurrences to concerned system services. In practice, such facilities bear three major limitations. First, only a part of the notification interfaces are exposed to user space apps. As a result, we cannot simply build an app to capture failures. Worse still, the reported events may contain false positives. Finally, the simple logging leaves out critical in-situ information for an in-depth analysis. To practically address these challenges, we customized the vanilla Android system for continuously acquiring system-level traces upon failures. The resulting system is called Android Mode. Android Mode targets to realize three important objectives: system service instrumentation, fine-grained system-level tracing, and failure recovery monitoring. Specifically, to instrument system services and collect system-level traces, we build a failure monitoring service into Android Mode. Once an event occurs, it pulls important base station, radio, and protocol-related information from concerned system services. For failure recovery monitoring, Android currently measures data store by examining if there are 10 outbound TCP segments, but no inbound segments in the last 1 minute. However, such fixed detection time can cause up to 1 minute of error. Also, this simple measurement lacks critical network stack information, therefore leads to false positives. To address these issues, we devised a network state probing component that examines both the local network stack and the internet connectivity by sending probe messages, and then cross-validates the probing results to rule out false positives. Consequently, both our detection time and the incurred error are at most 5 seconds. With Android Mode, we invite all the 250 million Xiaomi users to participate. Finally, over 70 million users opted in. From January to August in 2020, we recorded 34 different device models, captured 2 billion cellular failures, involving 16 million user devices, 3 mobile ISPs, and 5 million base stations. With this dataset, we have multifault findings on phone, ISP, and base station. First, let's have a look at the prevalence and duration of cellular failures. We find that as many as 33 cellular failures occur to a phone on average. Also, the average failure duration can be as long as 3.1 minutes. Just imagine when your phone is out for 3.1 minutes during emergency. This is no doubt a problem that we should pay attention to. Intuitively, buying more expensive hardware should bring us better experience. However, we surprisingly find that both the failure prevalence and frequency tend to increase with better hardware. To understand this, we examine the correlations between failure events and the phone model's features. Consequently, we uncovered two major impacting factors: 5G capability and Android version. As shown here, both the failure prevalence and frequency are higher on 5G devices than non-5G devices. We attribute this to the high workload 5G modules inflict on the network stack of Android, as well as today's still immature production state of 5G modules. For Android version, we find that despite quite a few new improvements, Android 10 in fact suffers from more failures than Android 9, most probably due to the better stability and the robustness of Android 9. Also, as Android 10 adapts to the emerging 5G technology, considerable new features were added, inevitably bringing defects to cellular data connection management. One such example is the blind prioritization of 5G in Android 10. This strategy might bring unstable performance and even cellular failures when your 5G connections have much lower signal strength than 4G connections. In fact, this is not a rare case in our everyday life. Also, by examining the code of Android 11, we find that the situation is not improved in even the newest system. As have been introduced before, data store is among the major types of cellular failures. To address the problem, Android has developed a 3-stage progressive data store recovery mechanism, which sequentially tries lightweight to heavyweight operations to fix the problem. Before launching each operation, it waits for 1 minute to check whether data store has recovered. However, while Android waits for 1 minute, most victim users would often manually reset the data connection within 30 seconds if the connection does not recover. Therefore, the probation process is rather inefficient. Apart from findings related to Android phones, we have also provided the analysis regarding radio access technology and receive signal strengths. Cellular failures are found to be less prevalent on 3G base stations, probably because 3G faces less resource contention today. For signal strengths, we surprisingly find that excellent signal in fact does not equal reliable connection. We uncovered that the prevalent excellent RSS failures mostly come from densely deployed base stations around public transport hubs, where ISPs usually densely deploy base stations so as to cope with large volume of human traffic. However, this special strategy could also make mobility management highly complicated and challenging, leading to more prevalent failures. With all these findings regarding widely employed techniques today, again we ask, what can we do about cellular failures? Our first idea is to devise general guidelines for the future policies of both phone vendors and the mobile ISPs. For example, we advocate the recent campaign of cross-ISP infrastructure sharing, which aims to achieve better coordinated base station deployment among different ISPs. We didn't stop here. As the collaborator of a major phone vendor, we further explore opportunities of enhancing cellular reliability in the real world. One such practice is improving Android's RAT transition strategy. Targeting Android 10's blind prioritization of 5G. In our design, we instead take the likelihood of cellular failures into account. For transition cases that could lead to a large increase in failure likelihood, we carefully avoid them to ensure reliability. In fact, we find that the avoided cases will generally not sacrifice data rate, but largely improve reliability. Also, we incorporate the novel 4G, 5G dual connectivity mechanism when applicable, which can maintain control plane connections with both a 4G and a 5G base station simultaneously. Therefore, when transition occurs, it can achieve smoother transition so as to reduce disturbance and improve reliability. For our second attempt of enhancing cellular reliability, we target the data store recovery mechanism in Android, as the original fixed time trigger is rather inefficient in practice. So how to find more proper time triggers? Our key insight is that the conceptual 3-stage progressive recovery in Android is essentially a state transition process. Therefore, we can formalize the overall recovery time with a Markov model based on the time triggers we use. However, we notice that traditional Markov process only describes a stationary process which has constant transition probability. In the real world, however, state transition actually depends on the elapsed time. To account for this, we adopt the time-inhomogeneous Markov process, or TIMP, to model transition in a time-sensitive manner. The TIMP model takes automatic recovery during probation process into account and uses a time-based function to model stage transition. With TIMP and our dataset, we can formalize our goal into an optimization problem. By solving the problem, we can then find the theoretically optimal triggers we pursue. In collaboration with Xiaomi, we patched the 2 enhancements in Android mode and further invited opt-in users to install. This time, 40% of the users upgraded and evaluated for 2 months. As a result, failures occurred 40.3% less frequently on the 5G phones, owing to our stability-compatible RAT transition strategy. Also, data store duration is reduced by 38% on average for these users, thanks to the TIMP-based flexible data store recovery. In conclusion, we conduct the first large-scale measurement of cellular reliability in the wild, where we identify critical factors affecting cellular reliability and build on our insights to develop enhancements that yield real-world impact. Also, we have released our code to the community. You can check it out in this website. Thank you.
Thank you, Han. So we have a couple of questions for you. So first question is from Nivya, and the question is, do you think it is possible or it is worth to repeat these experiments after the pandemic? Especially given that we will expect more mobility, once the restrictions are off. So do you think that is something that is worth repeating, or is it even possible to do that? How? You're muted. I don't know if you're trying to answer. I'm not sure. I think the author, I can see the author around, but I think he's muted. I'm not sure if he's listening to the questions. Okay, I guess maybe we'll take these answers, or like how can answer these questions over Slack, and we can move on to the next talk then. So the next talk is a variegated look at 5G in the wild, performance, power, QoE, and implications. So we have two, like presenters and authors jointly giving a talk as well as answering Q&A. So we have Arvind Narayan, he's a PhD candidate in Department of Computer Science at University of Minnesota. And we have Xiumiao Zhang, he's a fourth-year PhD student at University of Michigan. Arvind is more interested in 5G mobile networking measurements and network data science. And Xiumiao is broadly interested in networking and mobile system with a current focus on 5G networks. So can we start the presentation for Arvind?
Hi, my name is Arvind. In this talk, Xiumiao and I will briefly introduce our work titled A Variegated Look at 5G in the Wild, Performance, Power, and QoE Implications. Commercial 5G has been around for over 2 years, and operators are continuously expanding and upgrading their 5G deployment. Reports suggest that 5G adoption is going to hit 1 billion by next year. This is not surprising given the hype 5G enjoys, as well as the exciting use cases promised by it. However, there exists a vacuum in understanding how 5G as a technology performs out in the wild. For instance, little is known about the power characteristics of 5G. Is it more energy efficient than its predecessor 4G or LTE? Are there any trade-offs? What about 5G's network performance footprint? 5G ecosystem is continuously evolving with different deployment strategies such as non-standalone or NSA 5G, which relies on LTE for control plane operations, and standalone 5G, both of which are here to stay. Coupled with the low, mid, and high band frequency ranges, the 5G ecosystem has become complex to understand. Therefore, we also seek to improve our understanding of 5G's network performance and identify potential issues. Lastly, it's unclear how 5G will impact application quality of experience or QoE, and what could application developers potentially do to leverage 5G technology. To answer these questions, we build a holistic testbed consisting of different 5G smartphone models, external power monitors, etc. Using multiple 5G carriers, we carry out extensive in-field experiments in 2 US cities and conduct a comprehensive measurement study. We have released the dataset and measurement tools. We begin by first talking about the end-to-end network performance. A typical end-to-end path includes the end user or UE connected to the carrier's base station, which is then connected to the carrier's core. The core further acts as the gateway to the internet. Prior work has typically deployed virtual machines in public and private clouds to conduct end-to-end network performance tests. However, due to the known ultra-high bandwidth capacity of 5G, the internet can become a bottleneck affecting our experiments. Our goal was to understand the network performance provided by the carrier's infrastructure in different 5G deployments. But academic researchers like us do not have visibility into the mobile carrier's infrastructure and the policies enforced by them. To overcome these challenges, we take the following approach. Ookla's speed test service is a popular tool for testing network performance. All 5G carriers in our study hosted their servers on Ookla's speed test service. For example, as shown here, Verizon hosts around 48 servers in the US, which are typically located in major metropolitan cities. We leverage the flexibility of server selection provided by Ookla, as well as the carrier's presence to reduce, if not eliminate, the impact of internet-side bottlenecks. First, we look at the latency characteristics of Verizon's millimeter wave 5G. With the UE's location fixed in Minneapolis, we measure latency across all their servers in the US. When tested with the closest server located in Minneapolis itself, we observe lowest latency of just 6 milliseconds. The latency increased by over 2 times when tested with the second closest Verizon server located in South Dakota. Going to either coast increases the latency by a factor of approximately 10 times. We also conduct similar experiments on Verizon's low-band 5G and LTE network. Due to the flexibility in frame structure and control over the transmission time interval in 5G NR, both low-band and millimeter wave 5G exhibits better round-trip times than LTE. Nonetheless, our results clearly quantifies the importance of edge. We conduct similar experiments to measure throughput over millimeter wave. When multiple connections are used, the UE can achieve an impressive downlink throughput of over 3 Gbps across all the servers in the US. However, with a single TCP connection, even after tuning TCP, we find that the downlink throughput degrades as the distance between the user and the server increases. These results again signifies the importance of edge, especially for bandwidth-hungry applications. It also highlights the issues that exist today with current TCP layer mechanisms. The uplink throughput, on the other hand, peaked at around 220 Mbps. Both single and multiple connection tests can achieve peak performance across all the servers in the US. We also conduct network performance and handoff analysis of T-Mobile's low-band 5G services, which are deployed in both standalone and non-standalone modes. We skip them here, but the details can be found in the paper. Next, Shumya will talk about the power characteristics of 5G.
Hi, I'm Xumiao Zhang. Now, let's take a closer look at the power characteristics of 5G. We first investigate RC state machine. RC is a power management protocol. UE transitions between different RC states, including connected and idle states, to balance network performance and power consumption. In SA5G, a new inactive state is introduced for more efficient state transition. Using RC probe, an RC state inference approach integrated into our management tool 5G tracker, we infer different states and timers for different network settings. Please refer to the paper for the detailed results. We further studied the impact of state transitions on power consumption. When there is no network traffic, the US radio stays active for a period of time before entering the idle state. We find that 5G consumes more power during this tail period than what used to be experienced over 4G. And this number is especially high for millimeter wave 5G. Also, the additional switch from 4G to 5G when the UE promotes to the connected state on the NSA 5G incurs a large amount of power consumption. All this indicate 5G is less efficient in state transitions. Many recent works rely on software API for power readings. To use a hardware power monitor for more precise measurement, we have to remove the smartphone battery and reconnect the battery logic board to the monitor. Besides, the monitor requires an external power supply, so we carry a portable power station together with the laptop. We conducted in-the-wild experiments by walking through a loop with several 5G towers. We also conducted a controlled experiment by hand-holding the smartphone at a fixed location with clear line of sight to a 5G panel. From the control experiments where we set different target uplinks and downlink throughput during data transfer, we can learn that power increases linearly as the throughput increases, but the power of UE on the millimeter wave 5G increases at a slower rate. Basically, millimeter wave 5G consumes more power than 4G and low-band 5G at low throughput levels, but it becomes more efficient after a certain threshold, around 200 megabits per second. Signal strengths also affect the power consumption, and 5G signal strengths can fluctuate frequently and widely. To better isolate the impact of signal strengths, we divide the throughput from the power to calculate the energy efficiency for different signal strength levels. The energy per bit drops as the signal strength gets better. Looking into the power throughput signal strength relationship, we can conclude that both throughput and signal strength can significantly affect UE power. With the recorded network band information, we also see different bands have varied power characteristics. All the above findings motivate us to seek for a better way for the UE power model, while traditional approaches mostly consider only a single factor. We turn to machine learning-based, data-driven approaches to take into account multiple factors. Specifically, we use decision tree regression. We constructed power model for different devices, different networks, and different radio technologies and bands. By comparing the mean absolute percentage error averaged across all the network settings, our model, considering both throughput and signal strength information, produces the lowest prediction errors at 5.4%. Now, Arvind will cover the rest.
Thanks, Shumya. Next, we look at the QoE implications, beginning with video streaming. Adaptive bitrate algorithm is one of the primary tools used to optimize the quality of experience for streaming videos. From the existing literature, we picked 7 diverse state-of-the-art ABR algorithms and put them to test. We focus on 2 metrics here, one bitrate and second video stall time. The desired sweet spot is achieved when the bitrate is higher with lesser stall time. For 4G, we find several existing ABR algorithms work well and fall in the sweet spot. For 5G with millimeter wave coverage, most algorithms do well in achieving bitrate level but suffer with the stall time. On average, we find that streaming over 5G increases the stall time by approximately 58% when compared to 4G. There are 2 main problems causing ABR to suffer over 5G. Number 1, many ABR algorithms rely on throughput predictors to make bitrate decision, but the wild and frequent throughput fluctuations in 5G degrades the prediction accuracy, leading to non-optimal decisions. Secondly, an ABR algorithm makes coarser-grained decisions about the chunk quality based on the information it has, with no ability to roll back, say, a non-optimal decision once it's made. In the paper, we propose a simple 5G-aware interface selection scheme for video streaming that can help reduce the stall time without significant loss in quality and at the same time improve energy efficiency. Next, we also consider web browsing application as a case study to understand performance versus energy efficiency trade-offs between 4G and millimeter wave 5G. We find that 5G provides marginally better performance. 4G, on the other hand, uses much lesser power. Therefore, depending upon the radio band and technology, indeed we find a trade-off between performance and energy efficiency. However, challenges lie in deciding which interface to use to load a web page. This might be driven by the desired QoE. More details on this with simple models can be found in the paper. Coming to the key takeaways, we quantitatively reveal the importance of edge over the end-to-end network performance across different radio technologies, 5G carriers, and deployment models. We also highlight key challenges in meeting ultra-high throughput demands. In terms of power, we find that due to the complex ecosystem of 5G, there are several factors impacting power and energy efficiency. We also provide key insights into how upper layer applications should best utilize 5G by balancing the critical trade-off between performance and energy efficiency, as well as become 5G aware. Last but not the least, our study also provides motivation and research opportunity to design intelligent radio or band selection schemes that can meet the desired application QoE efficiently. To conclude, in order to reveal the state-of-the-art landscape of the 5G ecosystem, we conducted a comprehensive measurement study of the commercial 5G services here in the US from and across 3 key dimensions: network performance, power, and application QoE. Thank you.
Thank you, both the authors. And we have a bunch of questions for you. The first question is more about the Ookla server selection. So, can you explain a bit more about the Ookla server selection? Do you specifically select server in Korean network, or do you let speed test find that? And I'll pin that with another question that we have related here, is that, do you think that the methodology that you have is, making sure that you're only measuring the edge performance and you're able to bypass the, the transport network or the internet issues with the measurements?
Sure. Yeah, thanks for those questions. Yes, so Ookla allows us to select a server. So they list a bunch of servers and you can select which server you want. So for instance, for the Verizon test, we select, okay, Verizon located in Minneapolis, and then we can conduct a test and it will give us all the metrics like throughput, latency and stuff. Then we can move on to some other location and conduct another test. So yeah, it does gives us this flexibility. Secondly, how confident are we in avoiding the internet side bottlenecks? I mean, for sure, we cannot say like we have avoided or not, because we are doing these experiments out in the wild. But in the appendix, you'll see that within the state of Minnesota, we selected all the speed test servers and then selected. And we see that the carrier server was like performing best, and all the other servers had a 10% degradation. So, I mean, there are clues. I mean, we can point out and see them, but for sure, we cannot say that we have completely avoided the internet side bottleneck. But at such speeds like 3.3 Gbps, we believe we've sort of, we're looking at the peak numbers here. Yeah.
Okay, so we have a lot more questions. So we have a question about your, about power measurements. So Andhra has this question that, how did you measure that given mobility? Were you carrying the monsoon power monitor while you were running measurements with being mobile?
Yeah, hi, this is Xumiao. So yes, we carry the mouse and power monitor and connect the power monitor to the smartphone while we're doing the power measurement. So the current, like the modern smartphone has like put a challenge on the power management because the vendors tend to make the phone like all-in-one model. Like we have to remove the back cover, which is removable, and also the battery, and we instrument the smartphone and connect it to the Monsoon power monitor, and we will carry the power monitor and together with the power supply when we are doing the experiment, we handhold the smartphone and to work around the loop we set previously. Yeah.
So Shumei, another question for you. The power consumption for two operators look quite different. So any insights as to why?
So we did observe that like across different operators, across different models, the power consumption can be different. So that's why we model we constructed the power model for different such settings or combinations. So
okay. And question for you, Arvind. So what congestion control was used in the TCP measurements?
Yeah, so we did not change it. It was cubic. So whatever was the default, we kept it as it is. Yeah.
Okay. All right, so let's thank the speakers one more time, and we can move to the next talk, which is the last talk of this session, where we will be listening from Zi Hong, and he'll be talking about how we can democratize cellular access with Cellbricks. Zi Hong is a computer science PhD student at University of California, Berkeley. He's advised by Scott Shanker and Sylvia. His research interests lie in the broad areas of systems and networking. And prior to Berkeley, he received his master's degree from MIT and bachelor's from Michigan, as well as Shanghai's Yadong. So let's start the presentation, and then we'll have Q&A after that.
Hello, everyone. Thanks for being here. My name is Zi Hong. I'm a PhD student at UC Berkeley, advised by Professor Silver Nasri and Professor Scott Shanker. Today, I'm excited to be here to talk to you about our work, democratizing cellular access with Cellbricks. This is a joint work with my colleagues Silver, Mark, Shadi, Silva, and Scott. We started this project with a simple goal in mind, which is to grow the tending cellular. Cellular network is getting more and more important nowadays, having globally speaking over 5 billion subscribers, contributing to over 60% of internet traffic. However, despite the growing importance, today's cellular ecosystem is still dominated by a small number of mobile network operators, MNO. Such a monopolistic nature of the cellular market hurts innovation, pricing, security, and ultimately the user experience. Therefore, the goal of this work is to bring competition to cellular ecosystem by lowering the barrier to entry for new entrants. We would like players other than the major carriers to join the cellular ecosystem and profit from providing cellular access. We realize that the key to enable such a vision is to ensure that MMO with small to medium scale footprint can compete equally within the ecosystem. By small to medium scale footprint, I mean, for example, MMO covering a city, a village, a product, or down to even a single cell tower. By compete equally, I mean that a user should have no reason to discriminate between providers based on the scale of their deployment. Instead, we like to enable the user to consume cellular access from any provider that is available at a location and time, with no concerns of whether the provider provides services in other locations. With this goal in mind, we examined today's cellular architecture and realized that it's fundamentally at odds with the vision of empowering small-scale access providers. In the next few slides, I will explain why this is the case. Before we get started, I would like to clarify several cellular acronyms that will be used in today's talk. MMO, as mentioned before, stands for Mobile Network Operator. I will sometimes use the term operator or access provider for it. MVNO, which stands for Mobile Virtual Network Operator like Google Fi, and I will use the term Virtual Operator for it. And UE, which stands for User Equipment, and I will use the term user to refer to either the user or the user's equipment in the talk, depending on the context. In this example, we have two operators, both of which have large deployments. Let's now walk through an example of how today's user use cellular service. Before the user can obtain any cellular service, the first thing they need to do is to sign up with one of the operator and establish a contractual relationship with it. Such a pre-established trusted relationship allows the operator to be responsible for a set of user management functions such as AAA, authentication, authorization, and accounting. After signing up with the operator, the user can now attach to the network with the authentication function implemented in the management plan of the operator. Once the user is attached, you will be assigned an IP address, and then you can go to the internet. Later, if the user moves to a different location within the coverage of the operator, the network will migrate from one cell tower to another via handover. Such a handover requires in-network coordination between cell tower, and the cellular core to essentially make sure the user's IP address remains unchanged during this process. By doing so, the user's connection will be maintained, and this is usually referred to as a seamless mobility experience. Later, if the user moves further away and get out of the coverage of its operator, assuming the operator has a roaming contract with the other operator, the user is able to roam into the other operator's network. Roaming is an effective way to allow the operator to expand its coverage. However, there's a downside of roaming, which is that the user is usually assigned with a different IP address when in roam. This is because it's hard to maintain the user's IP address across provider boundary. And such a change in IP address usually leads to service disruption because for traditional transport protocols like TCP, the IP address is the unique identifier of the connections. However, this is not a severe issue for today because today's major operators have large footprints and roaming is rare, which means that users mostly enjoy a seamless mobility experience. As for MVMO or virtual operator, even though it introduced a new business model, it doesn't really change the underlying cellular architecture. The only difference is that instead of signing up with a physical operator, the user now will sign up with a virtual operator, and the virtual operator will then contract with multiple physical operators and offload most of the cellular operation to it, including the in-network mobility support. I would like to highlight two key properties of today's cellular architecture. Firstly, in order to achieve broad coverage, today's cellular architecture relies on pre-established trust. This means that users can only use cellular networks they have contracts with, either directly, which is the case when it's using its own provider's network, or indirectly, which is the case when you run into other operators' network or is using an MVMO service. Either way, pre-established trust is required before user can obtain access. Secondly, today's cellular architecture relies on in-network coordination for seamless mobility. However, while these two properties suit pretty well for large-scale operator, neither of them actually supports small-scale access provider. To see why this is the case, let's see what happens right now if we have a large number of small-scale access providers in the system. In this example, we show 4, and let's see whether we can use today's approach to achieve broad coverage. If we follow the convention and have the user sign up with one of the operator, because the operator itself has a very small footprint, in order to provide its user with satisfactory coverage, it has to establish all roaming contracts with all the other small-scale operators. However, this leads to high transaction cost of manually establishing all these roaming agreements, which is definitely unscalable. Note that MVMO doesn't solve this issue. The only difference here is that instead of having the operators establishing roaming contract in a pairwise fashions, the MVMO need to now go ahead and establish agreement with all the small-scale operators, which still incurs large transaction costs. So today's approach cannot work for broad coverage for small-scale access provider. How about seamless mobility? What happens right now is that with a large number of small access providers, moving user will frequently cross the boundary of different providers. As mentioned before, when crossing provider boundary, it's hard for the network to maintain the IP address of the users. Such a frequent change in IP address then leads to severe disruption in the user's services. In summary, today's architecture can provide small operators with neither broad coverage nor seamless mobility. Realizing the drawbacks of today's cellular architecture, in this work, we propose a new cellular architecture named Cellbrick to systematically address this issue and being able to scale to a large number of small access providers. Next, I will show in a high level how one could come up with a design of Cellbricks in a step-by-step fashion. In Cellbricks, we have users and we have a large number of B telcos of any scale. B telcos are similar to operator today, but we introduce new terminology because as it will become clear, there is a fundamental difference in terms of the function they support. So Cellbricks, the first design choice that we make is to start from the MVMO architecture. This is because decoupling service provider from access provider ensures that users are no longer bound to any small-scale access provider. Therefore, we introduce an entity broker here, which is similar to MVMO, but with some fundamental functional differences. Users sign up with the broker, and the broker is responsible for representing the user towards the B telco. The user then subscribes to the broker's cellular services and need not be aware of which B telco he attached to, which will change over time. B telco will be paid by the broker according to the amount of traffic it has carried for the broker's user. Next, we depart from the MVMO architecture in order to support broad coverage and seamless mobility. For broad coverage, instead of having the broker to establish contract with all the small-scale B telco, we embrace an on-demand and untrusted relationship between broker and B telco. Here, untrusted means that the broker do not need to have contracts with the B telco, and on-demand means that the broker only establishes a relationship with the B telco when one of its users requests to attach to the B telco. To support such an on-demand untrusted relationship, we need architectural changes. Specifically, now that the B telcos are untrusted, we can no longer count on them for implementing user management functions like authentication and accounting. Therefore, we move the user management function out of the network into the broker and user. By doing so, the Celbrix is able to use untrusted B telco in an on-demand fashion to achieve broad coverage. How about providing seamless mobility? As explained earlier, crossing provider boundary incurs IP changes, which is really hard to address within the network. Therefore, what we propose is to instead embrace IP changes and to move the support for mobility out of the network into the end host. End hosts now explicitly handle the IP changes caused by mobility instead of relying on the network to hide them. By doing so, Celbrix can provide seamless mobility without tight in-network coordination. This is it. This is basically the Celbrix architecture at a high level. We decouple service provider from access provider, like MVMO, and we move support for user management and mobility out of the network for broad coverage and seamless mobility. To recap, the goal of Celbrix is to enable on-demand cellular access from any available access provider by requiring no pre-established trust with the B telco and no in-network coordination between the B telcos. Celbrix come with many potential benefits. Firstly, Celbrix lower the barrier to entry for new access provider. B telco of any scale can make profit by providing cellular access within their coverage without establishing a large number of contracts. Secondly, Celbrix allows any user to use any access provider, which leads to a more efficient use of the infrastructure, as well as provide the user with high cellular availability. Lastly, Celbrix significantly simplified today's cellular call by moving the support for user management and mobility out of the network. With all these potential benefits, one question that naturally arises is that, is Celbrix technically feasible? With our research, we show that the answer is positive. Celbrix is technically feasible and its benefits come with minimal performance overhead. To demonstrate the technical feasibility, we designed 3 technical pieces to tackle 2 main challenges in realizing Celbrix. The first challenge is to support user management function without requiring pre-established trust between the broker and the B telco. For this, we propose a secure attachment protocol based on standard public key authentication schemes, as well as a verifiable accounting protocol based on embedding management function into the user spaceband, as well as a reputation system. The second challenge is to achieve seamless mobility without in-network coordination. For this, we propose a host-driven mobility solution, which is based on leveraging modern transport protocols like MPTCP or QUIC to handle IP changes. To evaluate the performance overhead of Celbrix design, we conduct 2 sets of experiments. Firstly, we measure the attachment latency in a small-scale physical testbed. Secondly, we emulate Celbrix host-driven mobility solution in existing cellular networks and measure application performance. Both experiments show that Celbrix introduced minimal overhead. More information can be found in the paper, including Celbrix detailed design and evaluation, related work, our answer to some adoption-related problems, as well as open questions regarding the market structure and business incentive of Celbrix. To conclude, Celbrix is a radically different cellular architecture that lowers the barrier to entry for new operator and enable a simpler and more efficient cellular infrastructure. Celbrix achieved this by moving the support for user management like authentication and accounting out of the network into broker and user, and moving mobility support out of the network into end host. With our design and evaluation, we show that Celbrix is technically feasible with minimal performance overhead. We open source the implementation and artifact of Celbrix to facilitate researcher and practitioner continuing working on this idea. That's all. Thank you.
All right. Thank you, Zio. So I have a question for you from Andra, and she says, thanks for the work, very interesting. And she's curious to know, how does your solution compares to the model that Twilio and M2M platforms propose?
That's a good question. I have to say, the name didn't ring a bell. So for that too specific for Twilio and other, I need to check the related documents. But in general, as highlighted in the paper, the way we departed from traditional MVMO architecture is basically requiring no pre-established trust and basically move the mobility support out of the network. And we believe that neither of the prior work rely on this to scale to a large number of small access providers. But I would definitely check the product or the document that you mentioned.
So I think while we are waiting for more questions, I have a question for you. So Cellbricks is enabling, it's trying to democratize access or like being able to operate these cellular networks, right? So do you expect like expert operators running these networks or non-expert operators running these networks? And is there overhead of managing these networks is going down with Cellbricks, or that is getting even harder for those operators to manage with Cellbricks?
The vision is definitely to make their life easier, because as we highlight, we'll move mobility support and management out of the network. So essentially, the access provider, what they need to do is a data plan and a control plan related to the data plan. So ideally, we want it to be as simple as possible. So it should be feasible for non-experts. And also, because we move mobility out of the network, mobility testing is one of the challenges in integration testing in today's cellular architecture. So I think by hopefully moving that, we can also reduce some of the complexity. So to answer your questions, we are still on the way, but the vision is definitely to enable anybody to be able to join the market, right? And in a way so that they can be competitive and also make it at the end benefit the end users with more innovations and maybe better quality of the services.
Okay. So we have a few more questions, a lot more questions. So a question from June, and he's asking, do you think host-driven mobility is going to use more resources on the device, and that's going to be a bit of a demotivating factor for transitioning or using Cellbricks?
That's a great question. Basically, we believe that it should not be a problem, because if you read the paper, the way we achieve most of host-driven mobility is by leveraging protocols like MPTCP and QUIC, both of which are already widely adopted actually in mobile platforms. And in principle, what they try to do is try to handle IP changes in an effective way. And that's if you in terms of energy efficiency, I don't think that's that expensive, because handover doesn't really happen that frequently, and it's basically just terminate the previous connection and restart a new one in an efficient way than manually doing so. So I don't think that's a concern, but it's definitely worth starting whether in terms of energy efficiency or other aspects of the solution. Yeah.
All right, thanks. I have one more question from Anna, and her question is, for your host-driven mobility, do you assume all servers support multipath, or where do you place the mobility anchor?
That's a great point. So for MPTCP, it requires no changes. Basically, for MPTCP, yes, it does require you to either have a proxy that supports MPTCP or have the server supporting MPTCP. The same thing happened for QUIC. So this, and well, I would highlight that the principle of Cellbricks is to embrace IP changes. So you can imagine this can happen over a VPN. It doesn't have to always happen in the transport protocols, right? A VPN, as long as it can handle IP changes, it fit into the overall framework of Cellbricks. But to answer the question, yes, for our current proposal for transport protocols like MPTCP and QUIC, it does require the server to support it. But the good sign is that both of them are actually getting adopted, especially QUIC. So I think this is my answer to the question.
Okay, and I have one question from Sun Wei Cho, and the question is that what incentives are there for telco operators to support Cellbricks, right? Especially if they need to change the existing system at all.
That's a great question that get asked. It was asked so often that we have a section in the paper actually try to answer this. We believe that we try to argue that there are some reasons for even for the incumbent operators to support it, because in high level, because running infrastructure is getting more and more expensive, and tacit sharing of this infrastructure is the trend, and so we basically enable them to do it more efficiently. But there is definitely likely that they will not like the idea of Cellbricks, because this is like increased competition and a threat to their monopoly positions. But the good side is that Cellbricks can be incrementally deployed in the sense that we do not require cooperation or help from the existing operators. In some sense that they may not like it, but there's nothing they can do to stop it. So this is, in short, the answer. But we definitely have a longer paragraph in section 3 trying to answer this question. And more generally, the business incentive or the market structure of Cellbricks is open to future work and discussion. We hope that we can inspire more work in both industry and academia to start to think about these problems.
All right, I'll thank the author one more time. And so I'll quickly transition to Hao. He was the author and presenter for paper 2. And, because of some connectivity issues, he was not able to join back then. So I would like to pose some questions before we end this session for him. So the first question is, it's from Nivya. And the question was about, is it worth repeating these experiments given the pandemic and given the mobility patterns are going to change or have already changed?
Yeah, that's a very interesting question. As I have mentioned, our measurement was from January to August in 2020. So our measurement results should generally represent the post-pandemic scenarios, I believe. But I think it's still interesting to revisit our results after the pandemic, as there may be some traveling boom after people are confined to their home for such a long time. Maybe there are more interesting issues coming up.
Okay, and we have a question from Ajay. He's asking, did you look at the software releases on Xiaomi devices and how many issues were fixed with new releases? And so there are a lot more questions, but maybe you can answer this one and I can ask more later.
Okay, I find that many questions are related to this one. They are wondering whether our results are specific to Xiaomi's software design or hardware design. I believe that our results should largely remain irrelevant to Xiaomi's specific software and hardware design and the configurations, because they are more closely related to Android internals and ISP infrastructures. For other Android vendors, such as someone has mentioned in Slack, like Samsung and other phone vendors, I believe our results are still reproducible on their devices as long as they stick to Google's vanilla Android design. And for ISP side issues, I think they are applicable to other vendors as well.
All right. Thank you once again, Hao. And that ends the session, technical session 10. And now we will be transitioning to around a 20-minute break, and we'll be regrouping at 11:20 p.m. PT to 20 p.m. ET. And that session will be networking for machine learning, and it will be chaired by Mushraf. All right. See you folks later.